All right, so at the top of page 369, we have three things that we're going to keep in mind as we go through this section and some of the other future sections as well. We're going to talk about these in depth today just to make sure that they kind of make sense, and then we'll get into some examples. So the first thing that we've been talking about in terms of these integrals is you can think about integrals two ways. Okay, area under the curve of whatever function is listed here, or you can think about an integral as an antiderivative, meaning working backwards. If you were to work backwards from velocity, what function would you have? If you go backwards, yeah. Position. Okay, so we know if we work backwards from velocity, that would represent the position function, and our bounds are from A to B. So notice how if we were to plug in top bound of B minus bottom bound of A, okay, that fundamental theorem of calculus, we would get the position at B minus the position at A. So if you're taking one position and subtracting another position, you're basically finding the change in position, aka how far you've traveled. Does that make sense? Change in position? For instance, if I start at this block, bless you, and I end at this block, okay, my change, if you count them, would be 3 blocks. Okay, a distance that you've traveled. But there's two different types of distances that we need to discuss. There's something called net distance and total distance. And they can get a little confusing. So to kind of make sense of them, I want you to draw a graph on this left-handed open section here. We're going to say this represents the graph of velocity. And maybe we'll make note of some of these x-intercepts. We'll just say they're 2 and 7. Can you tell me, based off that velocity graph, when the particle is moving to the right? Good, Dan?
Any point from 0 to 2.
How'd you know?
Because it is positive.
The velocity is positive. Notice how the velocity graph is above the x-axis. So if velocity is positive, the particle is moving to the right. What if the velocity is negative from 2 to 7? How's the particle moving? Maybe we'll talk about left and right motion, because I know you can also do up and down, but maybe we'll just do left and right. If velocity is negative, it's moving left, okay? So at this point of 2, you have that kind of change in direction. What do you think if the particle is moving to the right from 0 to 2, what do you think the area under that velocity graph represents? The area under a curve, aka an integral, aka working backwards. Go ahead, Dan.
Distance to the right.
Okay, so if this is the interval where the particle is moving to the right, the area under the velocity curve is representing how much it moved to the right. So we'll say amount moved to the right. Can you guys see that green? It's a little, I can see it on here, but sometimes for the camera it's a little vague. Okay. Very similarly, we said from 2 to 7 the particle was moving to the left because velocity was negative. If you were to find the area under that curve to the x-axis, that's the amount it moved to the left. Okay, that change in position, how much it moved from 2 to 7 in this case. So if you were to add together the amount it moved to the right and the amount it moved to the left, that's what's considered your net distance. You might be more familiar with a different term, specifically if you took a physics class. Do you know another word that is a synonym to net distance? Yeah. Displacement, right. Basically, how far you are from your starting point. All right, now a little side note for this one. If the velocity is always positive, meaning if you were to get rid of this kind of lower part here, notice how the displacement is also the total distance. Because if all of this is the amount you move to the right, and you're not changing direction, you're not moving to the left, this is just how much you've traveled overall. Displacement gets a little tricky because you're going to have some of these different intervals where you're moving to the left and you're moving to the right. It's when you take all of them into consideration, you're going to eventually figure out how far you are from where you started, okay, aka displacement. So we can figure out displacement by simply integrating velocity, okay, figuring out that change in position. However, if we wanted to figure out total distance, let's say this area amount was 3 and this area amount was -5. Could you tell me what the displacement was, how far you are from where you started? We'll say this was 3 units and -5 units. What's the total area of those two curves? Yeah, -2. So wherever you're starting, you're 2 units to the left of where you started. That's your displacement. If you move 3 units to the right and 5 units to the left, what was your total distance that you traveled? Good, Dan? 8. You see how the negative doesn't matter anymore? Okay, because for total distance, we don't care if it's moving to the right or to the left. We just care how much you're traveling. So that's why when you look at this notation, do you see how it has an absolute value in there? Don't absolute values get rid of negatives? Okay, so for total distance, we're going to take the integral of the absolute value of velocity because we don't care if the area under the curve is negative, meaning you're moving to the left. We just want to know how much you're moving to the left. Okay, so just to be safe, kind of when it says here, whenever you're asked for total distance, we're going to use the absolute value velocity, okay, integral, unless we know for sure that the velocity is always positive, because in that case, we don't need the absolute value. So what we're going to do is we're going to keep referencing these 3 things as we go through this section. Okay, I hope that they make sense. If you work backwards from velocity, you get position. That change in position is your displacement, how far you are from where you started. But if you were to work backwards from the absolute value of velocity, that's representing your total distance. Are we okay so far? Do those 3 things make sense? All right. The first one we're going to try is a non-calculator. Okay, so let's go ahead and say the velocity of a particle is moving along the x-axis. So that means you're moving left and right. And its velocity is modeled by that equation. Okay, if the position of the particle at time 4 is 72, what is the position at time 2? Let's go ahead and maybe rewrite these in mathematical notation. So in terms of function values, we could say the position at time 4 is 72. And we're trying to figure out the position at time 2. If they give us velocity and we're trying to figure out something about position, we need to work backwards. Okay, use some type of integral. So how might you want to set up that integral? Can we figure out the function? Can we figure out the bounds? What do you think, Joseph?
2 to 4.
2 to 4, good.
3t squared plus 6 equals p of 4 minus p of 2.
There we go. All right, so if you were to integrate velocity, aka work backwards, you would have the change in position, top bound minus bottom bound. change in position. All right, now on this right-hand side, we know what P of 4 is. That was 72. And we're trying to figure out P of 2, so we're going to have to leave that one blank. Okay. On the left-hand side, this is when we got to figure out kind of the area under this velocity graph. Now, we don't have a graph to actually calculate, like section it off into triangles, trapezoids, circles, rectangles, whatever the case is. We're going to have to do this one by hand. So let's go ahead and work backwards by hand. If you have a 3t squared, what did you have previously? Antiderivative, yeah.
T cubed.
T cubed, perfect. And if you have a 6 now, what did you have previously? A 6x or a 6t, yep, whatever variable you're using, looks good. And we need top bound minus bottom bound. Okay, now we don't have a calculator, so let's think about this. We need 4 cubed, 4 times 4 times 4. 64, good. Plus 6 times 4, which would be 24. Okay, so that's what we get if we plug in the top bound. And then we have to subtract what we get when we plug in the bottom bound. So 2 cubed would be 8, and 6 times 2 would be 12. All right, so from there, we should be able to figure out what P of 2 is, okay, where we were located on this x-axis at time 2. So 64 plus 24 is 88, minus 8 is 80, minus 12 is 68. So it looks like P of 2 would be 4, right? 72 minus 4 is 68. All right. Do you see how the setup of this question was very similar to what we talked about in the last section? Okay, it's just that we're applying it to velocity and position, okay, some type of meaning behind the functions. Let's go ahead and check out part B. What is the total distance that the particle travels from 0 to 7? Okay, notice that word total distance. So just to be safe, we're going to try the absolute value of velocity. So we're going to integrate from 0 to 7 of the absolute value of velocity. Do you know how to work backwards without a calculator from an absolute value function? Have we talked about that this year? Do you know how to find a derivative of an absolute value or integrate an absolute value? We haven't done that, okay, and we're not going to do that. So here's the thing. If you really think about plugging in any value from 0 to 7 into this velocity function, would you ever get a negative value? No, right? So if you're never getting a negative value, you're never moving to the left, meaning the particle is always moving to the right. If it's always moving to the right, all of the area is going to be above the graph. You're not going to have any of this negative area to worry about that you have to take the absolute value of. So in terms of integrating it, since it's always positive, okay, above the x-axis, you don't really have to write those there. So just to be safe, I would start with them, but then if you think about if there's any number that would make it negative and your answer is no, you can remove them because the absolute value doesn't really do anything. So let's go ahead and check this out. If we were to work backwards like we did before, okay, we found the antiderivative in the previous question, that would be t cubed plus 6t. And with different bounds, we're just going to plug in the 7 and then the 0. Again, we don't have a calculator, so we got to do 7 times 7 times 7. Anyone figure it out? 7 times 7 times 7? Yeah?
343.
343, good. All right, so 343 plus 6 times 7, which would be 42. And then we got to subtract what we get when we plug in 0 for those t's. But we'll get 0 for both of them in either case, which is nice. So it looks like our total distance is 385 units. And we were always moving to the right. Okay, so we always move 385 units to the right. Do we understand why we were able to take the absolute value away in that case? Specifically because we were solving it by hand? Okay, let's go ahead and try a calculator example. All right, the velocity of a particle moving along the x-axis is given by that function. Do you notice how the function's a lot more complicated than the one we just did? Kind of makes sense why this one would be a calculator example, because we can use this to help us out drastically. Okay, if the position of the particle at time 1.5 is 2.551, what's the position at 3.5? So maybe we'll rewrite this information in function notation. The position at 1.5 is 2.551, and the position at 3.5 is what we're trying to figure out. So they give us velocity, they're asking us about position, that means we have to work backwards, aka integrate. What might your integral setup look like? Can we figure out the bounds? Can we figure out the function? Let's see, did we write the bounds as 1.5 to 3.5? Sound about right? Okay. And the velocity function is 0.5 e to the t minus 2 cubed. And if we work backwards from velocity, we get position. But we'll need the position of the top bound minus the position of the bottom bound. All right, now we don't know P of 3.5, we're trying to figure that out. P of 1.5, we know that. How do you think we'll calculate the left-hand side? We did it by hand in the previous example. How do you think we can calculate the value of this integral? Do we remember how to do it on our calculator? Remember what buttons to press? Go, Dan.
Yeah, I gotta go to math and hit the integral button.
Yep, math, and then it's down to option 9, INT. So we're just going to type in exactly what's on our paper, the bounds, the function. I know on your paper it has t's, but on your calculator you'll just use x's. .919. Okay, so that's the left-handed side of this equation we have, and looks like we can solve for the position at 3.5. We'll just add over the 2.551. So to 3 decimal places, we'll have 18.470. We doing okay? Too fast, too slow, just right? I feel like Goldilocks. Yeah? All right, let's try the next one. What is the total distance? Okay, so we're going to have to integrate the absolute value of velocity. Some of that area might be negative. We don't want it to be negative, so we're going to change it positive by using an absolute value. Now, when we were doing this by hand, we had to think about, is there a value, oh sorry, wrong bounds. Is there a value between the bounds that would cause the velocity to be negative? Now, in the previous example, we said that there wasn't one, which was nice, because then we could work backwards by hand. But since this is a calculator question, you don't necessarily have to ask yourself that question, because we are able to do integrals of absolute values on the calculator. So we're just going to go straight to our calculator for this type of question. So on your calculator, let's go to math option 9 again to bring up the integral. Our bounds for this one are 1 to 5. But in the function spot, we want to do the absolute value of the velocity equation they give us. Do you know where to find the absolute value bars on your calculator? No? Okay, we're going to go back to math, but this time you scroll over to number, and it's option number 1, ABS, short for absolute value. So if you hit that option, it should automatically throw in the bars on your screen. So inside those bars, we're just going to go ahead and type in the velocity function. Looks like we get 913. Does that look about right? Okay. So 913.067. Okay. Now, if you really look at this, okay, are the absolute values needed for this question? Can you think of a number between 1 and 5 that would make this absolute value negative? The inside negative? If you plug in 1, isn't 1 minus 2 negative 1, and then to the third power that's negative 1? Wouldn't that make it negative? But if you plug in 5, 5 minus 2 is 3, 3 cubed is 27. That's positive, right? So there's some spot in this interval where some of the area is below the x-axis, some of the area is above the x-axis. We just want to make sure all of that area is positive. That way when we add it together, we get the total distance traveled. So the absolute values are definitely needed for this question. And it's nice that it's calculator because we can just type it in and we're good to go. All right, let's go ahead and try some other ones. At least for this one, we'll be pertaining to a graph. So for the next one, the graph of velocity measured in feet per second, units might be nice to know, of the particle moving along the x-axis. We're moving left and right. The position of the particle at time 8 is 12. Maybe we'll write that in function notation to help us out. Use the graph of velocity to answer the following questions. All right, what is the position of the particle at time 3? Do you guys want to talk this one out, or do you think you want to give it a try? I see pencils moving. It's a good thing. All right, let's check it out. They give us the graph of velocity and they're asking us about position. So what do we need to do? Do we need to take a derivative or do we need to work backwards, aka antiderivative? Antiderivative, right. Okay, so if you think about the order, you have your position function, then velocity, and then acceleration. So if you're starting with velocity and they want you to work or find position, notice how you have to work backwards, aka antiderivative. So we're going to integrate velocity. What are the bounds? In terms of the x-axis, which represents time, we're going from 3 to 8. And if we work backwards from velocity, we know we get position. So maybe we'll write P of t. Now some of you might be already used to writing on this right-hand side P of 8 minus P of 3. That's what would happen after we do that fundamental theorem of calculus. So we'll do P of 8 minus P of 3. Now this left-hand side, we've kind of done a few different ways so far. The first example we did, we worked backwards by hand because we didn't have a calculator. The second example, we worked backwards using a calculator because we had that advantage. But notice how we don't have an equation to actually work backwards from. We do have a graph. So how do you think we'll have to calculate the integral from 3 to 8 of the velocity function? What are we specifically looking for on this velocity graph to fill in this left-hand side? What's one definition of an integral? Yeah. The area under, specifically this velocity curve. Okay, so we're going to go from 3 to 8. So we got to figure out all this area. What are some geometric shapes you might want to use? Yeah.
Two triangles and right thing.
Okay, so we have this triangle down below. CV wants to section this off again into another triangle here and then a rectangle. Sure, we could do that. Some of you might realize that this is a trapezoid and want to do a trapezoid and a triangle. That's okay too. We should always get the same thing. All right, so let's try Stevie's. His rectangle has a base of 1 and a height of 5. So we need base times height. Stevie's other first triangle has a base of 2 and a height of 5. So 1/2 base times height. His other triangle has a base of 2 and a height of 2. But notice how it's below the x-axis, right? So this area is negative, aka we have to subtract it. All right, so let's see, we have 5 plus 5 minus 2. So we get 8 for the total area under the curve. Do we know what P of 8 is? The position at time 8? 12, good. And we're trying to figure out the position at time 3. So 12 minus 4 looks like would give us 8. So the position at time 4 is 8. Oh, sorry. The position at time 3 is 4. Messed that up. This 8 is representing your displacement. How far you are from where you started. Specifically at this time of 8, you started at 12. So you're 8 units away. Notice how if you go backwards 8 units from 12, you get 4. Because this 3 is backwards in time from that 8. All right, let's check out B. What is the acceleration at time 5? They give you velocity. They're asking you about acceleration. So do we need to take a derivative or do we need to take an antiderivative, aka integral? If you think about your order. Derivative, good. Okay, so what are we specifically looking for on this velocity graph to help us figure out the acceleration at time 5? We need the derivative of this velocity graph at 5. Derivative, aka slope, right? If we go to time 5 and we were to plot a point, we need the slope of that point. So what does that slope kind of look like? Can you do rise over run? Bless you. Maybe use the two endpoints to help you out. Remember, pick a point before it, after it, calculate the slope. What'd you get? Yeah.
-2.5.
-2.5, good. Did you write units?
Feet per second squared.
Awesome. Feet per second squared. Acceleration unit, we need a squared unit in the denominator. Great. All right, what is the net distance, aka displacement? How far you are from a starting point. That the particle travels from 0 to 10. Go ahead, Dan. What'd you do?
I took the integral of 0 to 10,
Uh-huh.
which you could split because there's two distinct shapes, 6 to 10 and 0 to 6, which would be the trapezoid and the triangle.
Okay.
And you add them together.
Perfect. Okay, so you have this. Which trapezoid did you use? 0 to what?
The trapezoid. 0 to 6.
0 to 6. Okay, so you found this area,
Yep.
and then you added that area.
Yep.
Okay, so displacement, aka net distance, is just the area under the velocity graph. How far you are from where you started, that change in position. So let's see, the area for a trapezoid, we need 1/2 times the height, meaning the distance between your parallel sides. So that height looks like 5 times the sum of the bases. So your first base looks like a distance of, what is that, 2? And the second base has a distance of 6. All right, so there's the area above the x-axis, aka how much it moves to the right. We now have to subtract the area below the x-axis, which is a triangle. So 1/2, the base would be 4, and the height is 2. All right, so this area below the x-axis is how much it moves left. Let's see, 2 plus 6 is 8, 1/2 of that's 4, times 5 is 20. 1/2 of 4 is 2, times 2 is 4. So it looks like its displacement or change in position is 16. What about units? Remember, this is a distance, how far you've traveled. Do we know what our distant unit is? Feet, good. All right, let's try the last one. What is the total distance the particle travels from 0 to 10? Can we set up our integral? Our bounds are from 0 to 10. Total distance, we're going to change something ever so slightly, yeah.
Absolute value of
There we go. All right, so how do you think we'll calculate the total distance? Yeah.
Instead of doing 20 minus 4, you're just adding both of them.
There we go. All right, this area beneath the x-axis is negative. We don't want it to be negative, okay, because we want to figure out how far we're moving overall. So instead of 20 minus the 4, we'll have 20 plus the 4, so a total distance of 24 feet. So even though you're only 16 feet from where you started, you actually had to travel 24 feet in order to get there. You did some backtracking, because notice how we started to move to the right, but then we moved to the left. Okay, we had some change in direction. How are we doing so far with velocity, acceleration, working backwards? Okay, we'll try another one tomorrow. Okay, this time we'll look at a table example, but we'll stop there for today. Yeah. Did you? Did you need to do part 1 then? It's part 1.